Good morning, everyone. Welcome to the Good Vibrations seminar number 11. This morning, we'll have a seminar on PMS delta Scutis given by Thomas Steindl. And I asked Paul Beck to introduce him. So Paul, the floor is yours.
Thank you, Rita. I have the pleasure of introducing Thomas Steindl, who is a PhD student at the University of Innsbruck in Austria. He is team member with Constanze Zwins, and in his PhD work, he is working on improving the understanding of the early evolution of stars, both in observations and stellar modeling. And therefore, the topic will be tidally perturbed pulsations in the Riemann sequence delta Scuti star of RS Cha.
So thanks for the introduction, and also thanks for having me here today in this great seminar. I hope my screen share is now working. And as introduced already, I'm talking today about our recent work together with my supervisor Constanze Zwins and also Dominic Baumann, who is a collaborator on that work. It's about tidally perturbed pulsations in the Riemann sequence delta Scuti Binary RS Cha. And when we talk about tidally perturbed pulsations, that first we need to talk a bit about self-driven pulsations. And overall, if we talk about self-driven pulsations in binaries, then there are some effects that can alter the structure of the frequencies that we can observe in an amplitude spectrum or in Fourier analysis of these systems. So first of all, there is a light travel time effect. And simply from the orbit, the stars will be in different distance from the center of mass, depending on the orbital phase. And then also there will be a difference in distance from the star's position and the position of the observer, may it be on the Earth or in a space telescope like TESS, for example. So this leads to an arrival time delay, from which we see a splitting of the frequency in the amplitude spectrum and also some phase delays. And we can use that, for example, it has been used and can be used to find binaries, to find planets even, and to constrain the orbits. Another effect on self-driven pulsation in binaries is the existence of trapped pulsations. So amplitude modulation can be experienced by stars that are tidally distorted. And as such, you can have a relative mode amplitude that is dependent on the orbital phase, and with that also a mode phase that is dependent on the orbital phase. So this would, again, solidify itself as a multiplet of frequencies that are split in the amplitude spectrum with once the orbital frequency. And then the third effect that I want to talk about here is tidally perturbed modes, which are presenting in this case for RS Cha. And in principle, if we have a binary that is synchronized and circularized, and we have an equilibrium tide that influences the mode cavity, and as a result splits the degeneracy between the eigenfrequencies of the same degree. And that then leads to, we go from an unperturbed eigenfrequency to, depending on the azimuthal order, we go to different mode frequencies. And this is dependent on the degree of the mode itself. So for radial modes, we don't have any splitting there, of course, and no changes in the frequencies. And for example, for degree L1 modes, we have a splitting for M1, and absolute value of M is 1 mode and M0 mode, so they will split apart. And besides that splitting, if we go to the observer's frame, so the frame that we are looking at when we use test data, for example, then we have an additional splitting of these frequencies. So depending on the azimuthal order and the mode degree, we have different signatures that are of frequencies, of multiplets of frequencies that are split either by twice, as we see in this case, or once the orbital frequency. So in principle, by finding the signatures that are dependent on the azimuthal order and the mode degree, again, we could use this to do some mode identification. And this is something I will talk later on a bit. So moving on, there has been some evidence in the literature in the past for tidally perturbed modes, and here's just a bit of a summary of what is out there and what you can find. So here's, for example, an eclipsing binary star composed of a Scuti and a gamma Dorado star was presented by Hamilton in 2013, and what you see here is kind of a shell diagram of the pulsation frequencies as a function of the pulsation frequency modulo the orbital frequency. And what you see here is that we have multiple occasions where around a pulsation frequency with a higher amplitude, there are other frequencies that you can find in Fourier analysis that are split by the orbital frequency. So here are a few, here again. And this is something that, as Bologna stated out, can be interpreted or should be interpreted as tidally perturbed modes. And then Bologna also presented another distinct case, so another couple of observations of a delta Scuti star or a delta Scuti a binary with a delta Scuti component, where we have again these high amplitude modes that then have other frequencies that are split by the orbital frequencies. There is other evidences or other cases. For example, Dominic Bowman presented the case of Ogru, where we have an amplitude spectrum where we see very nicely here these frequencies that are split with the orbital frequency, since we have the red lines show us the orbital frequency and multiples of that. So we see here a really nice splitting with exactly this frequency. And then recently also in other types of stars, so we have here P5 Orionis, and this is a work by Jaszkiewicz last year with bright observations where they found frequencies that are split by twice the orbital frequency, and that it was interpreted by them as the sign of L1M0 mode, and for that they are the first kind of that use this as a way to identify modes. Beside the ones that I've shown you here, there are also some others that I just put down here as a reference, where I don't want to go any more in detail. Now, today I'm talking about RS Cha, the primitive sequence delta Scuti binary. So I want to give you a small recap on what is the literature stand, or what was the information that we had before our work came out. And it was discovered as slightly variable in 1960. And later, a few years already, the binary nature was discovered and the eclipsing nature. And it was originally assigned as an algal type or beta Lyrae type eclipsing binary star. Then 1967, there were the first orbit determination. And a few years later, Jorgensen found that the components are almost equally bright, and this is something that holds true until now. It's a binary system composed of two stars that really are rather similar. Now, then in 1977, the first short period variability was discovered, and the first idea that this could be pulsations. And it took not long after that for Clausen and Nordstrom to find out that both components of RS Cha are actually delta Scuti stars. And then there was kind of a gap in the literature that is available for the system until Mamacek gave us the information that it is indeed a primitive sequence star, since it's part of a cluster that is young enough that stars with these masses have not had enough time to reach the zero-age main sequence, and as such burn hydrogen in the core equilibrium as stars on the main sequence do. By some work by Alcyon and collaborators, we have the knowledge that it is a circularized and a synchronized orbit, which is of course really nice, since the theory by Reniers and Zmeyers about tidally perturbed modes is mainly focused and gives analytic approach and values and formulas for this specific case. And they also did some detailed stellar modeling, from which we now have a really good idea about the evolutionary status. And later after that, in 2009, we have from Böhmetal, we have a first detection actually of pulsation frequencies. Namely, what they did is a spectroscopic time series analysis that then not only gave us frequencies, but also mode identification. And this is also something that's important later on. The last important literature happening for RS Cha was that Woolens found a third component with high probability that is most likely a red dwarf that is really, in terms of brightness, much less bright than the other two stars. And then, of course, there's a paper we released or was published this year, beginning of this year, about the tidally perturbed modes and the evidence for that we see in the test light curve. And I'm going to look forward to what will be done with this system, either by us or by other authors in the coming years. So let's have a look at the observations of the TAS observations of RS Cha. What we see here is sector 11, 12, and 13 in Shortcut and Steindl. We see, of course, the eclipsing binary natures as the light curve in these black dots. And then what we see are the gaps in the data that are really typical for test data. So we have the gap in between orbits for the data downlink, and then there are some parts here and here where basically stray light from the Earth and the Moon is influencing the light that or the light curve, or the quality of the light curve, and as such the pipeline basically removes it. So this is the SRP light curve, because the PD-SRP correction introduces some instrumental effects that will change the out of eclipse phases and just move it around. So we used the SRP light curve for that. If we zoom in, especially to the out of eclipse phase, then we can already see that there is short period variability on the time scales of a few hours, clearly indicating the existence of pressure modes. Well, what we know is, again, it's a circularized and a synchronized system, and overall it's really well studied. So we have the idea, or we have the values for the stellar and the orbital parameters, which means, as we can see here, it's really two really similar stars with a similar mass, a similar radii, similar effective temperatures and luminosities. And together with the orbital parameters, it is not difficult then to use a code like Phoebe, which is the next generation Wilson-Davini code to model eclipsing binaries, to then create a model for the eclipsing binary light curve. That is obviously something that we need in order to properly investigate the pulsation spectra of this star. So what you need to do is you do some modeling of the light curve, and then you remove that and have an iterative approach to then model the pulsations, remove them from the original light curve, and have this iterative approach until you have a good model for the binary, and you can then investigate the pulsation on its own. And again, as I said before, we have a good knowledge about the evolutionary stages of RS Cha, or of the primary and the secondary. And what we know is that they're on the first onset of the CNO burning. So what that means is that in this plot, you have a Hertzsprung-Russell diagram of the later parts of the primary sequence evolution. And what you see is basically at the end of the Henry track, we obtain higher central temperatures that are hot enough to burn the C12 that is initially abundant in the stars into an NO14, but we cannot move on with the next step of the CNO cycle. So this leads to the creation of a convective core, and then to this burning of this initial C12, but it's not hot enough to really go and burn the CNO in equilibrium. So what we have then is that once the C12 is basically down to equilibrium abundances, we kind of stop this burning, and we have to heat up again until we are able to really finally ignite, see the full CNO cycle, and then at this point we are at the CRH main sequence. So this line shows you where the abundance of C12 has dropped to a value of 10 to the minus 4, and we just see that this is the position of two models for RS Cha A and B that are at the same age, have the same radii and the same masses as the values that are depicted in this table. And this just gives us a really good idea on where we are in the evolutionary stages. Now let's move on to the pulsations in RS Cha. So in this plot, you see different versions of an amplitude spectrum that corresponds to a light curve that is on the right side here, phase folded with the orbital periods. We have the total light curve, so with the eclipsing nature and the pulsations. Then the one where we have removed the pulsation, the eclipsing nature of RS Cha, and then also where we mask the times during the eclipses. What we see here in the amplitude spectrum is in black the amplitude spectra, and this blue lines show you the orbital frequency and multiples of that. And of course, if we look at the total light curve, you see most signal and only more or less signal eclipsing nature, and have peaks here at 2 and C. However, if we remove this binary nature, this eclipsing binary part of the star, what we end up with having this beautiful delta Scuti pulsation amplitude spectrum. And we see pulsation signal, especially between 10 and 15 cycles per day, and then 18 to 30 cycles per day. But if we look at the phase-forwarded light curve, then what we see is that especially during the secondary eclipse and also during the primary eclipse, what we have is that the amplitude of our pulsation signal is diminished. And this is something that we can or should expect, since we have a changing light ratio due to the eclipsing nature, when of course the primary blocks the light from the secondary or parts of the light, then the frequency or the amplitude of a frequency that star is pulsating with will be diminished during that phase. And we also see that in a comparison of these two light curves where we have masked the eclipses, we see that the amplitude of the frequencies in the amplitude spectrum change a lot. So this is something we have to keep in mind in our future or in the subsequent analysis. So we have taken the full pulsation light curve, and we have applied a Fourier analysis and found 108 significant frequencies. And within these frequencies, we got two kind of combination frequencies. The first one, of course, the ones that we expect in nearly every delta Scuti stars that has abundance of pulsation frequencies, namely frequencies with other pulsation mode frequencies. So we just have a combination of A times Fy plus minus B times Fj. But there is also another combination, and this is basically that we have a combination between one frequencies and then an integer times the orbital frequency. And this is exactly the same evidence as we have seen in the previous examples for tidally perturbed modes. Now, similar to the previous example, we've also created this kind of a shell diagram where we have in this lower panel here all the frequencies above 8 cycles per day as plotted as a function of the frequency modulo the orbital frequency. And we see a lot of these instances where we have multiplets of pulsation frequencies or frequencies that are spaced by once or twice the orbital frequency. For example, here, or here, and really a lot of abundance of these occasions. In the upper panel, you see the signature that are expected for tidally perturbed modes dependent on the azimuthal order and the mode degree. So for radial modes, for example, we only expect one frequency. For degree 1 and azimuthal order 0 modes, we expect 2 frequencies that are spaced by twice the orbital frequencies, and so on. And if we look at that, then we are able to see exactly these signatures in our shell diagram. So we have 16 times the occasions of the L1 M0 mode. That is again 2 frequencies spaced by twice the orbital frequencies. And then we have 4 occasions of the signature of an L2 M0 mode that basically is 3 frequencies that are split by twice the orbital frequencies. And in addition to that, we have here a multiplet that basically is out of 7 frequencies that are split by once the orbital frequency. If we drop 2 of the low amplitude modes, then we would end up with the signature of an L2 M2 mode, or if we include them, we have a signature of an L2 L3 mode. And this is exciting because going back to what is in the literature, if we look at the Bermetz paper of 2009, then they found that there is a frequency which has pretty much exactly the frequency as one frequency in this multiplet. That is a pulsation mode of degree 2 or 3. And as such, exactly the same mode identification that we can create with the signature of tidally perturbed modes. And they know that this is from the secondary. So we try to kind of figure out which mode this originates from, or the signal originates from. And from that, we have to reinvestigate kind of the amplitude variations. And so we fitted the highest amplitude frequencies to subsets of our light curve to investigate how the amplitude changes with time. And for the first 3 frequencies, we get for F1 and F3, especially, that other than during the secondary eclipse, the amplitude is rather constant. And only during the secondary eclipse, there is this sharp decrease in frequency amplitude. So for the second frequency, we have a more kind of irregular structure to the phase-dependent amplitudes. As we see here, it's more irregular, but we also see this core message somehow that during the secondary eclipse we have another peak here. Especially if you look at F1 and F3, you can imagine yourself that this might be a decrease that you might be able to a Gaussian decrease during the time of secondary eclipse to these models. And this kind of motivated us to investigate how such phase-dependent amplitudes with this Gaussian drop during the secondary eclipse or during the primary eclipse would influence the light curves that we would obtain from such a system. And so we produced a toy model where we have this phase-dependent amplitudes and saw that light curves look really similar to what we can see in the light curve of RS Cha, as we have this drop in amplitude. That is also something that we've seen before in the phase light curve from the amplitude spectrum a few slides ago. Use this light curve and do a classical Fourier analysis, and we see that this also results in a splitting of the frequencies with the orbital frequency, and classical Fourier analysis also give us all these splitted out frequencies in as significant frequencies as well. So this led us then to produce this really toy model where instead of going from a traditional Fourier analysis that is just a linear combination of sine functions, we go to a model with phase-dependent amplitudes as this toy model, where we add sinus that is, instead of a constant amplitude, has this Gaussian drop during or Gaussian decrease during the time of either the secondary or the primary eclipse. And as such, we have to assign each frequency to either being of the primary or the secondary. And we do this in an iterative approach, similar to the classical Fourier analysis, where we take the light curve, we calculate an amplitude spectrum, we get the frequency and the amplitude of the highest peak, fit the single frequency. And now in a traditional approach, you would combine, take this frequency, combine with all the other frequencies, create a model, pre-writen the original light curve, and then check if there are more frequencies that are significant, and if you would cycle around, and if not, you're basically done with your analysis. Now in this way, so for this phase-dependent amplitude model, once we have our frequency and our amplitude, fitting the single frequency is not that simple anymore. So what we do is we need to create a model for the single frequency, both for the primary and the secondary. And then we use statistical criteria to decide which assignment fits better. So we then either assign a frequency to the primary or to the secondary, and then we go on, combine all the frequencies that are either then in the primary or the secondary, and pre-write in the light curve, look if there are more frequencies, and then are in this iterative approach until there are no more significant frequencies left, or basically we have some ending for our modeling. If we do this, we end up with a different set of frequencies, and we end up with the information of where we believe or this model attributed this frequency to, so either the primary or the secondary star. And this is what we end up with, right? So we have the same Echelle diagram. We have more or less the same frequencies. We've lost a few low amplitude frequencies, but we have gained an information about the origin of the pulsation frequencies in this toy model. And for example, if we look at the signal of F2, if we compare that to the classical Fourier analysis, then what we have is that we've lost these two low amplitude frequencies that are not anymore in our list of frequencies that we get from the model. And we have now five frequencies that are split by once the orbital frequency, and these are all assigned to the secondary, even if none of the assignments or none of the frequencies know of the assignment of, let's say, the mother frequency, which is the one with the most amplitude. So for every one of these frequencies, independent of all the others, we have assigned this frequency to the secondary. And this really gives us a good idea that F2 originates from the secondary same conclusion that also Berman about 12 years ago. So now we have the signature of an L2 mode that is originating from the secondary, and we get this, and as such the same conclusion as these previous analysis. And this, of course, is very exciting for our for kind of the truth, the start of our analysis, and also kind of a verification for the analysis of Berman collaborators in the past. Now, if we also look at the multiplets around the first frequency F1 and F2, then we see that we lost a lot of these low amplitude frequencies, and the multiplets kind of aren't really multiplets anymore. Instead of 5 here, we are just with 2 left, and instead of 10-ish here, we are just with 3 left. And this, together with the information that we saw in beforehand, or so the phase-dependent amplitudes, where we have had this Gaussian drop during the secondary eclipse, leads us to believe that actually the multiplets that we can find for these frequencies are most likely emitted or basically reaches the telescope because of the light, part of the radiation during the eclipses. If we move on and basically look in other parts of this diagram, we see that we have multiple occasions of these signatures where we lost in this new model here low amplitude frequency and have the other two still there, and then identification still is influenced by this binary effect, or by this effect of the eclipses, and as such we will need to have a more physical model of the binary dependent, the phase dependent amplitudes because of the eclipses, to really reinvestigate this mode identification and make it, let's say, more sophisticated. But it is really a nice thing to view again, that for a lot of cases here, the assignment of the frequencies to either the primary or the secondary is the same for both or all of them in a multiplet. So for example, here we have 2 that are both assigned to the secondary. Here, this L1, M1 signature is all assigned to the primary, for example. Of course, there are others where we have different assignments, but in essence, this just tells us that we have an influence from the phase-dependent amplitudes due to the changing light ratio, and we need to keep that in mind when we do mode identification. I want to use the last few minutes of my talk basically to put RS Cha a bit in context overall for the Prima sequence astroseismology. And so I want to show you here a plot from the paper from Swins et al. Of 2014, where they found that there is a relation between the highest frequency that is excited in Prima sequence delta Scuti stars and its evolutionary stages. And RS Cha A and B have been part of this sample already, as they are marked here in this plot. And you see in the background, these are the models that have been calculated by David Gunter with the RIREX evolution code. And it is now independent of which evolution code you use, but you have to discuss the model that goes in behind that. And the classical Prima sequence evolution is, I would say, something that we should think about to improve that for future endeavors for our future analysis of Prima sequence stars. Because if we look at our classical Prima sequence model, then our initial model is a huge gas of ball that is fully convective. So in this animation, I show you in the background, you see the evolutionary track of a 2.5 solar mass star in this classical Prima sequence evolution. And you see here a model of the star where we basically just cut through it. The color code is the logarithm of the temperature, and these hashes tell us which part of the star are convective. And for comparison, here on the lower left, is also the size of Sun. Our initial 2.5 solar mass star is about 60 to 80 solar radii in size. And then this is what the Prima sequence evolution in this classical model looks like. We contract fully convectively along the Hayashi track. until we lose the convection in the center of the star, get a radiative core that then starts to grow until the full star is radiative, and we are moving along the Hennier track. We're hot enough to ignite this CN part of the CNO cycle, as we've seen before, have this drop, move on to get hotter until we reach the zero-H main sequence. Now, again, these initial models are really unrealistic in size. And
can you hear me? Sorry. I was just wondering if you could maybe turn off your video, because your camera, because the connection seems to be quite bad, and there's a problem with the sound. Maybe it will.
Oh, I'm sorry about that.
Okay, no worries. Thanks.
Okay, thanks for reminding me and changing that setup. So again, if we want to discuss these models, then we kind of have to have an idea where these models come from. And I want to argue that these initial models that we use are just unrealistic. So it would be a good step to go to more realistic initial models. And what we know is that star formation happens in molecular cloud. The collapse of molecular cloud leads to the creations of stellar seeds, where we have protostellar seeds that are also called second Larsen's core, for example, where we have about 10 Jupiter masses and something around 1 to 5 solar radii. So here is, for example, a model with 10 Jupiter masses and as initial values and 1.5 solar radii. And these then accrete material from the surrounding disk or from a surrounding cloud until they have enough mass accreted that they then basically stop accreting for different reasons and have these 2.5 solar mass accreted, and then are similar to other stars. So what we have here is the beginning is also very convective, and then we have a convective core, radiative outer, radiative outerish part, and then again a convective envelope. And we would go on and then accrete material, gain a bit in size, and then we would have almost a flash-like deuterium burning that gives us a fully convective star almost again until the deuterium burning is over. And then we kind of move to converge with the classical evolutionary track that is depicted here in red. As you can see here also from the size of our sun is that the scaling is much different. So what that means is that we, in this model, or in this more realistic model of the primitive sequence evolution of this 2.5 solar mass star, we never reach these really high stellar luminosities that we assume for the initial model for the classical evolution. And as such, we never reach these high radii, we never reach these low density surface gravities, for example. So there's really a big change if we talk about the primitive sequence evolution of the classical model that we used in the past, and this, let's say, improved primitive sequence model that has not reached the field of astroseismology. And what we did in a recent work that is currently under review is to calculate models from this more realistic approach. And from that, you can see here we have an accreting track that basically accretes until it itself reaches the zero-H main sequence. And then from that, from this track, we can calculate the subsequent primitive sequence evolution that is depicted here in this thinner lines. And the colored areas here show you an instability study that we performed with Chaya, where we looked at which parts of at which region, which stars showed pressure mode that are that basically the growth rate tells us should be excited. And what we will see at first hand is that, if you know what I didn't tell you yet, is that these black crosses here are known primitive sequence pulsators, primitive sequence double Scuti stars, and the diamonds primitive sequence Gamma Dorado stellar Scuti hybrids. So you can mention, of course, that this low effective temperature area, there shouldn't be any excited modes. And yes, I would just ask you to ignore that. We have good evidence why this seems to be excited. And this is because we have the missing input physics, mainly from time-dependent convections. And hopefully the paper will be out soon, and you can have a more in-detail look about our arguments why we should also only view this hotter part besides this edge that is given here also as the real instability strip of our calculations. And what we see in the different colors are different areas of the Kiel diagram where we expect different amounts or different of radial orders for these pressure modes to be excited. And what you can also see here is that two of these stars again are the primary and the secondary of our delta Scuti premium sequence binary RS Cha. So with our mode identification, and if we then create a more sophisticated model of the phase-dependent amplitude, and as such can improve our mode identification and then investigate that further. With that, we hope that we can soon able to produce the radial orders, and then from there can really go ahead and test if these results that we gain from these calculations agree with the values that we find in real delta premium sequence delta Scuti stars. And with that, it is clear why RS Cha is really an important part, and it will be really important in the future of premium sequence astroseismology. And also with that, I want to come to my summary slides, where I just want to kind of conclude a bit what I've presented and what we've presented in this work. Mainly, we have that RS Cha is a binary, and it's composed out of two delta Scuti stars that are really similar in terms of stellar properties. And I think I hope I have convinced you that in this system, we see the best evidence for tidally perturbed modes yet, since we were able to perform mode identification, and also our mode identification agrees with a previous identification from spectroscopic time series analysis that is in essence really absolutely different. So we also performed the toy model where we used phase-dependent amplitude, kind of motivated from the amplitude degrees that we've measured from our light curve, so that the changing light ratio during the eclipses influences the amplitude of the frequencies. And from that, we also found that both the mode identification is changed a bit, and also the frequencies that we find change depending on whether we use this or not. But overall, we can conclude that both stars mainly pulsate in dipolar modes with azimuthal order 0. And finally, as I've hopefully made the case in the last few minutes, I think we have that RS Cha is an ideal specimen to test this theory of tidally perturbed modes by Reniers and Smayers, and then hopefully try to use some astroseismic modeling in the near future with these observations that then also include the effects of tidally perturbation. And of course, it will be important in the future of premium sequence astroseismology, and this is something that we are really looking forward to that. At this point, I'm done, and I'm happy to try to answer any questions you might have.
Excellent, Thomas. Thank you for a very interesting talk and for being on time. So I asked Paul to moderate the questions. I hope you are still able to do so, Paul. And feel free to ask questions on the chat or raise your hand directly.
Yes, so thank you, Thomas, for a very interesting talk on the premium sequence targets, which normally don't get a lot of attention. And I think your work will help to shed some more light and attention. And with this, I would open the floor for any question, which I'm sure there are plenty. If somebody's speaking up, we don't hear you because you're probably muted. Connie says that as usual, she lets the youngsters go ahead. And I agree with that. Well, then probably I take the first question as still young. Your improved model, how does it compare with cluster studies? You have the model on.
yeah, that's something that
we don't hear you.
In the first approach, this is we have to model the process, and this is no.
Thomas, we don't understand you. The connection is very interrupted.
Do you hear me now?
No.
Hello.
Hello.
Do you hear me?
Now it's better, yeah.
Wait. Hello. Okay. So to make sense for the how we treat the accretion process in these very young models. And we're still, so in this first paper that we hopefully will be available soon, we try to do this and then use spectroscopic parameters of non-primary sequence.
You're coming in very interrupted.
The influence on which I think what your question and also is targeting at is kind of.
Sorry, I didn't understand your question. Your answer, you came in very interrupted.
So Thomas is telling us that he's changing the Wi-Fi. Maybe you can go on the 4G if you have access to that.
Okay.
It can help.
In the meantime, let's collect questions.
Okay, so meanwhile, I could eventually, oh, there's a question by.
Okay, Vicky.
Hi, can you hear me?
Yes.
Yes, perfect. So I was trying to raise my hand, not to clap before, but apparently. Okay, so Mike, thanks for the nice talk, and I hope you can hear me, Thomas. I was wondering, you were showing this your slide with a range of excitation for prime sequence models. How does that compare to main sequence stars? Have you looked into that?
I think Thomas is actually just offline as he is.
Okay, that
offline.
Is then bad timing for my question.
Yeah, so let's wait for a moment that we see him to come up.
Okay.
Well, I guess those are the downsides of the new normality.
Yeah. Okay, let's wait for him to come back, hopefully. Changing the network might help. So I just wanted to point out again that if you missed a previous seminar, we have recorded them and you can access them through our website. Also, it's more or less automatically, thanks to Mikkel, put on the TASOC past event page also. So I've put the address of the website on the chat. If you want to retrieve past seminars, you can go there. Okay, so I cannot see.
Thomas is back online. Thomas, do you hear us?
I'm back. I hope, hopefully I'm back. Am I back?
Yes.
Yes, you are.
Yes.
Yeah, I've now changed to my smartphone. So I'm connected with my smartphone. I'm deeply sorry for that. So I will try answering the questions now without being able to show something. I hope that will work.
So maybe you can answer again Paul's question, and then Vicky has also another question for you. So
yeah.
Paul, maybe you can just repeat it because.
Yeah, my question was, how does your evolutionary track for the improved model compare with cluster studies?
Yeah, the answer to that is pretty simple. Is that is something that we're trying to do in the future. So from some quick looks, it does not much change the position of isochrones, for example, on the Hertzsprung-Russell diagram. But then this is something that is really dependent on the choice of input physics that we use to model the accreting process. So you have a lot of free parameters that come into play when you talk about these early parts of the evolution. For example, you need to fix or you need to choose the accretion rate, so the mass accretion rate. You have to choose the entropy that you give the accreted material. And this all will influence the position of your track in the Hertzsprung-Russell diagram. And so we hope that in the future, we will have time to investigate how this influences this stuff like isochrones. But then also what we know from literature, since besides from astroseismology, these models have long reached the literature state of the art of models. So this is one of the explanations, and especially together with episodic accretion, one of the explanations of the age spread that we find in young clusters. So dependent on the accretion history, we have that we have a luminosity spread, and then if we interpret it as terms of age, then we find that this explains the age spread that we find in some young clusters.
Okay, thank you. Then Vicky, could you please repeat the question?
Yes, thanks for a very nice talk. And sorry if you mentioned what I'm going to ask and I missed it. But can you explain how you showed at some point computations for the range of excited modes in primitive sequence stars? Could you maybe comment on how they compare to main sequence, to the range of excited modes in main sequence stars?
Yeah. So we did not do calculations for main sequence stars with the same setup, but we can compare the range that we kind of end up with. So the temperature ranges are quite similar. So when we look at also then on the observational paper from Murphy, where they find delta Scuti stars up to 10,000 Kelvin, this is also somewhere where our edge in a hot edge for the theory comes up. So this then translates for primitive sequence stars up to masses for up to 3.5-ish solar masses, which is a bit more massive than the main sequence models. But in essence, we are in a similar region. And then for the red edge, it's a bit difficult since we have this missing input physics. But this is
okay.
So there's something where we try on improving our modeling approach for that, maybe being able to maybe include also time depending.
Okay, thank you.
Then there were three questions via the chat. The first one was by Jürgen. Jürgen, would you like to?
Sure, yes, thank you. It was very interesting. And in particular, I'm very interested in these new models with core evolution and accretion, which have been discussed, of course, before, and I've never seen this in as much detail. So my question is, if you compare models of your star, in the two cases, the traditional and the new models, does the structure of the models differ in a way that would be recognizable in the frequency spectrum, such that we could actually use the observations of the frequencies to test between the two models?
Yeah, so that's an excellent question, and it's really an interesting answer to that. So if we look at the early parts of the evolution, we have really a change in the internal structure, especially in the way we treat the accretion process, since we add a lot of energy with the accreted material in the outer parts of the star. That means that we heat the atmosphere, and this then moves inside the star and leads to a temperature inversion. That then also means that especially that the cerium burning doesn't ignite in the center, but a bit off center. And also due to the change of accretion rate, we gain a lot of new material that can be used for the deuterium burning. So we get really change in structure. And in this early parts, this will definitely, this influences the frequency spectrum. And then with time, after the accretion has ended, the structure converges to the classical model, but there are still some differences in that. So some differences remain. And this is also something where we will now, don't want to say too much. This is something that we're working on. I don't want to jump to too early conclusions, but I hopefully I can refer you to future papers. That is really something that we currently might absolutely focus on how that we can really see the difference and how strong are these differences, and can we use that to gain more information.
Thank you, because of course there's a trade-off between the time the star spends in these very active, very different periods, and so the chances of catching a star with an oscillation signal in these early phases is quite small.
Yeah.
Whereas once you get close to the first carbon ignition, you do see the stars, and that's of course where ISK is. So the question is, and I certainly look forward to seeing the results of that analysis. So thank you again.
Thanks.
Thank you. The next question was submitted by Connie. Would you like to?
Yes, Thomas, thanks for your talk. Great work. A follow-up question on Jörn, maybe a bit harder question, because I think if I recall well that you have a lot of information. You have the inclination, you have the mode identification of 2 stars, and then you're testing new physics. But from the geometry, if that were the only reason why the amplitudes are different, it would be the reverse, right? You would expect higher amplitudes for the sectoral modes, if I'm correct. So can you use that to exploit the fact that some modes are more strongly damped than the zonal ones to tune your input physics of your new models? I realize this may be a tough, long question to answer immediately.
Yeah, it is. But I mean, the short question is, you're absolutely right. There's a lot of interactions, a lot of things that are at play here, and that we should be able to include in our models. And yes, we have the inclinations, we have that information. So what we would like to do, what I would like to do, is to put that all together, because we don't only have these ingredients. We have the changing light durations due to the eclipses. We have the inclination that is then dependent on the amplitude of our spherical harmonics. We have that, as we are in a binary, we might also have these tidal distortions that we have from the trap pulsations. So we should include that. And because we are as lucky as we are with RS Cha, we are circularized, we're synchronized. So we have an analytical approach to the tidal perturbation. And now if we throw all that together, I would love to investigate the mode identification in more detail, and then perform some astroseismic modeling and turning on these knobs, each one at a time, and then all together, and see what's the influence for that. I see this is the first step, has to be the first step, before then using that information as input physics for more detailed prime sequence models. But this is something, again, on the list. Hopefully I'll have the time to do it in future.
Okay, good luck.
Thanks.
And there has been a third question submitted via the chat by Cenk. Would you like to read your question out?
Paul, he says he has no microphone and asks you to read it, actually.
Oh, okay, I did not see that question. I didn't see the comment. Okay, so Chen Kayan says, great talk, thanks. Maybe you mentioned it, but I missed it. Which fundamental parameters of RS Cha did you infer directly from tidal pulsation frequencies? Yeah, I have not a mic now.
Oh, none. So the parameters are, we already knew that kind of from the literature. So there is studies for the radial velocity curves, and we have the light curve. So we have the stellar parameters and the orbital parameters, and then we use that to model the binary light curve. But at this point, we basically just present that we have the evidence for the tidal perturbed modes, and we did the mode identification. Then using this information, using that the perturbed modes to infer some more parameters is something that will then be possible, hopefully, in the approach that I just explained in the last question, when we use all these input physics, all this information together to perform astroseismic modeling. Once we have that, I think we can improve all the stellar parameters, the orbital parameters, and then if we also include mode excitation, maybe also some more parameters that may be able to constrain them.
Okay, I have a follow-up question on that. You said that the binary system is synchronized and circularized. What actually is the tidal excitation mechanism here?
There is no excitation mechanism, so that the modes are self-driven. So we have delta Scuti stars that, similar as non-binary delta Scuti stars, just pulsate as delta Scuti stars. And then we don't have a tidal excitation, but we have a tidal perturbation. So we change the mode cavity, and that perturbs the mode, and that then leads us to our spherical harmonics need to be changed, or the reference system need to be changed to have the same spherical harmonics. And this then leads to splitting in frequencies.
Okay, thank you. So light on the airport, we haven't traveled all together, but last call for questions, last opportunity. I take the silent as a no, and would like to thank everybody who participated in the questions, in the questionnaire, and also Stefan for a very nice talk. And
Thomas.
What did I say, Stefan? Thomas. And yield back to Rita.
Yes, thanks a lot, Paul, and thank you, Thomas, for a very interesting talk and a very good work. Well, I just would like to thank you all for being here with us, and I would like to remind you that in 2 weeks we have our last Good Vibrations seminar given by Joey Momberg, and he will talk about modeling of gamma door stars on a huge scale, I would say. So thank you all for being here. Thanks again, Thomas, for your time and effort. Sorry about the connection sound issues.
Yeah, I'm sorry about that.
No worries, it happens. See you next time. If the steering committee wants to stay around a couple of minutes, they're welcome to do so.
Bye.
Bye, everybody.
Bye, everyone.
Bye, Rita. Bye, everyone.
Bye.
Bye.
Thanks a lot.
Recording.
Mm-hmm.